Greetings from Istanbul Technical University. I'm Emir, the team lead of the IT Rover Team. With our 8 years of experience, we are ready for the University Rover Challenge 2024.
This year we designed the Rover chassis from aluminium tubes, which eases to assembly parts and makes it more durable. The Rover features a rougher suspension system with a differential rod to navigate obstacles and adapt to various terrains. The movement of the Rover is powered by brushless DC motors situated within the aluminium hubs of the wheels, providing protection against external factors. Also, we use 3D printing to manufacture the TPU wheels with ABS ring. The Rover has a length of 1.1 meter, width of 1 meter including the wheels, and height of 0.3 meters from the ground.
The power source of the Rover is a 42-volt lithium-ion battery. The different voltage values needed in the Rover provided by the power distribution board containing 4 different buck regulatory sequences that we designed. The drive system is controlled by brushless motor drivers using KNFT bus and vehicle control kit we designed. Precise control can be achieved with the PID, which can be configured thanks to the incremental encoder built into the motor driver. The emergency button placed at the back of the vehicle for accessibility is used to shut down entire vehicle. The triple light source placed next to the antenna, information about the Rover's operating mode can be obtained even under daylight.
2.4 GHz communications modules are used in long-range tasks, while 5.8 GHz modules are used in tasks that require high data transfer rates. Efficient compression algorithms are used to prevent USB and communications bottlenecks. Our user-centered interface is used to execute commands, display video feeds, and view scientific graphs. Bottles and mallets are identified by using custom-trained artificial intelligence algorithms. The Rover can perform a spiral search pattern to detect article text from a long range using our new algorithm. A state machine is implemented to be able to control and check the status of the Rover. Localization is achieved by the fusion of the data collected from RTK GNSS data through our custom-made GNSS module and our IMU sensor. A dual antenna configuration is then used to improve the heading of the Rover. A LiDAR sensor is used for creating point cloud data of the environment and the cost map used for obstacle avoidance.
We have designed a 6-axis robotic arm powered by self-manufactured servo mechanisms with BLDC motors. Aiming to minimize backlash and provide the necessary torque, we utilize belt drive and custom cycloidal gearboxes. The belt drive system enabled us to adjust the weight balance more easily when determining the position of our motors. Based on the analysis we conducted, to reduce weight, we made custom manufactured cycloidal gearboxes. Also used aluminum and carbon fiber material for robotic arm. Considering the diversity of tasks, we designed an end effector with flexible moment capabilities in all directions.
We are using field-oriented control to control our BLDC motors. Precise control is achieved by using the data received from our 14-bit encoders as feedback to our PID control loop. Communication between our motor drivers are obtained by KNFT bus. Combined with the USB to KNFT interface, our computer is able to communicate with the robotic arm directly. Additionally, an STM32-based custom PCB is designed to control the end effector.
Our robotic arm can demonstrate exceptional versatility and precision, capable of executing a diverse range of tasks. It utilizes inverse kinematic solutions within industry-proven frameworks with ROS, enabling control in both Cartesian and joint spaces. This enables the arm to manipulate knobs, press buttons, handle tools, and place items in drawer with ease. Furthermore, the integration of encoder feedback allows the robotic arm to adapt to dynamic environments, enhancing its ability to perform intricate tasks with heightened precision and efficiency. Additionally, the use of USB cameras simplifies the operation of the arm gripper.
In the science system we use this year, we have further improved the shovel mechanism. Thanks to the elevator system descending parallel to the ground, the required amount of samples can be collected. It is aimed to prevent contamination by using 4 separate diggers. In order to ensure efficiency in the process, filter containers were placed on the elevator system. The quick transfer onto the collected sample is provided by peristaltic pumps. We use a drilling mechanism to take deep samples. It can reach 20 cm below the ground and take samples from all types of soil, and thanks to its structure, it serves as a container.
As science team, our goal is to gather habitability indicators, atmospheric and subsoil sensors that can measure temperature, moisture, and more. We also intend to identify life biomarkers in the soil. To achieve this, we use a paper-based biosensor designed for glucose detection, utilizing inheriting tests to identify proteins and amines, and have developed a region for detecting ATP.
We use a compact spectrometer system that examines the early parts of the visible range to obtain accurate information about the concentration results from hydrogen and ATP region. We are also conducting mineral analysis with the newly developed 532 nanometer Raman spectrometer. Thus, in order to reduce the noise resulting from the fluorescence emitted by organic materials in the soil, we are using a number of physical techniques like photo-bleaching, computational methods like phase Fourier transform.
We placed the depth camera to scale the panoramic image of the stratigraphic section. As a second instrument, a high-resolution camera used, with close-up ability to understand structure of the rocks.
The overall geology of the landing site consists of Jurassic and Cretaceous age sedimentary members. Geomorphological features such as inverted channels and meanders have been observed in the region, pointing to an ancient fluvial sedimentary system, which indicates water existence.